Welcome to STEM Talk.
STEM Talk. STEM Talk. STEM Talk.
STEM Talk. STEM Talk.
Welcome to STEM Talk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society.
Hello, I'm your co-host Marcus Baumann, Director of Healthspan Resilience and Performance Research at IHMC. Joining me to introduce today's podcast is the man behind the curtain, Dr. Ken Ford, IHMC's Director and Chairman of the Double Secret Selection Committee that selects all of the guests who appear on STEM Talk.
Hello, Marcus. Great to be here. Today we have one of the world's foremost authorities on dietary protein and amino acids, Dr. Donald Layman. Don is known for his extensive research on muscle development as well as his studies of metabolic regulation with implications for obesity, diabetes, and cardiovascular disease.
Don is a professor emeritus in the Department of Food Science and Human Nutrition at the University of Illinois Urbana-Champaign. He spent 31 years on the faculty before stepping away in 2012. Much of Don's research over the years investigated the impact of diet and exercise on adult health problems, again related to obesity, type 2 diabetes, and metabolic syndrome. His lab at Illinois particularly focused on understanding how metabolism works. He conducted clinical trials for nearly 2 decades, helped create a new understanding regarding how to optimize people's macronutrient balance and metabolism. In addition to his work on metabolism, he has conducted extensive research on how to enhance body composition, energy levels, and monitor blood sugar. Today, he serves as Director of Research for the American Egg Board and is a nutrition consultant for the National Dairy Council and the National Cattlemen's Beef Association. He also is the Chief Science Officer of Qivana, a natural products marketing company that promotes the weight loss program that Don developed in his lab at the University of Illinois.
Before we get to our interview with Don, we have some housekeeping to take care of. First, we really appreciate all of you who have subscribed to STEM Talk, and we are especially appreciative of all the wonderful 5-star reviews.
As always, the Double Secret Selection Committee has been continually and carefully reviewing iTunes, Google, Stitcher, and other podcast apps for the wittiest and most lavishly praise-filled reviews to read on STEM Talk. If you hear your review read on STEM Talk, just contact us at stemtalk@ihmc.us to claim your official STEM Talk t-shirt.
Today, our winning review was posted by someone who goes by the moniker Carl Runner. The review is titled, "One Pod to Rule Them All." The review reads, "This is a high-quality podcast in that the bright, curious hosts interview the top minds in science and research regarding human performance and making a brighter future. They find ways to make STEM interesting to everyone, and you can see the personal side of the researcher. I am always impressed with the top-level science that is underway and how much it applies to every aspect of our lives. The multidisciplinary nature of this high-end work often provides consilience to much of my studies in medicine and wellness, but the podcast can also serve to better inform any professional."
Well, thank you, Carl Runner, and thanks to all other STEM Talk listeners who have helped make STEM Talk such a great success.
Yes, and you don't always see consilience used in a podcast review. Okay, and now on to today's interview with Dr. Don Layman.
STEM Talk. STEM Talk.
STEM Talk. STEM Talk.
Hello and welcome to STEM Talk. I'm your co-host today, Marcus Baumann. Today we'll be speaking with Dr. Don Layman, and joining me to introduce today's podcast is the man behind the curtain, Dr. Ken Ford, IHMC's Director and Chair of the Double Secret Selection Committee that selects all the guests who appear on STEM Talk.
Hello, Marcus, and hello, Don. Great to be here.
Hi, Ken, and great to meet you, Marcus.
Good to meet you as well. Let's jump right into it. Don, I know you grew up on a farm in a small town in northern Illinois. Tell us what that was like.
Well, it was a great experience. I learned a lot. I think growing up on a farm, you learn a lot about independence. I think I learned a lot about just being curious about things and also how to make things work. You're sort of independent. So it was a great experience, and I thought it was a great launch pad.
So how small was the town you grew up in?
Well, the town wasn't super small. It was about 13,000, town by the name of Qivana, but it had 2 different school systems, and I went to the smaller one that had less than 400 people at it. So I grew up in a very small town environment and lived out on a farm.
I'd imagine with only 400 people, you got to know everyone.
Yeah, your classmates across every all 4 years, you knew everybody.
So when you weren't doing chores on the farm or doing work for school, I understand you were playing sports. What kind of sports?
I particularly like football. I ran a lot of track and field type of things, but I grew up doing water skiing and sort of any type of thing I could get involved in.
When did you first become interested in science?
I was fortunate to have some really good science teachers, clear back to, middle school, 8th grade, and then on into high school. And I was always interested in why things worked and sort of the math and science of it. And so I was just, it was just always, I was going to go off and study science.
So after you graduated from high school, you headed off for Illinois State to study chemistry and math. Sounds like you were thinking you would become a chemical engineer or something along those lines. What happened?
I realized I wasn't nearly as good in math as I thought I was. I think coming in a small town, you have relative few experiences, you have fewer role models. And so I knew I wanted to do science and chemistry. So that was sort of the direction I thought. And, as you get into it, you realize your aptitude is in different areas. I once had a professor that I think it was inorganic chemistry. And I think his comment was, when you find what you're really meant to do in life, it'll be easy. And this isn't it for you.
So you develop an interest in biochemistry specifically. Do you think that partly came from growing up on a farm?
Yeah, I think that, I really like chemistry, and I found that my aptitude in organic chemistry and biochemistry to me is kind of a three-dimensional puzzle. And I love the sort of mechanistic aspects of thinking of pathways. And so, it was always intuitive to me, and I sort of drifted to it. And I had some great mentors along the way that kind of steered me along the path. So again, small town boy, horizons really weren't very far out there. And I just sort of was willing to go with the flow and figure it out as I went.
As you were studying biochemistry, you started looking into protein synthesis with a professor by the name of Arlen Richardson, who was quite well known for his aging research. Can you talk about this period and how your interest in protein and muscle evolved over time?
The interest in biochemistry, again, was interested in pathways. I got interested in kind of the process of protein synthesis, protein turnover, and was lucky to get in with Arlen Richardson, who was studying the aging process of protein turnover. And we were at the time studying liver, which, back the 1969, 70 era, we didn't have the techniques to do a lot of other things. So liver was easy to work with. And we were studying the mechanisms, and we realized with aging, there were a lot of changes. The number of ribosomes would go down. The messenger RNAs that were providing the message would change. We discovered the change in the poly-A tail, which basically is an aging process on messenger RNA. So it really got me thinking about all of these regulations. And protein synthesis is a very complex mechanism, and it's regulated in a lot of different ways. And I just found that fascinating.
So let's back up for a moment. Can you explain for listeners the importance of protein as it relates to metabolism and what you mean when you talk about protein turnover?
I think what surprises everyone, I think everybody knows that our body has a lot of protein in it. About 40% of our body weight is protein. But what people don't realize is we have this constant process of turnover. Most people think about protein for kids and they're growing, but the rate of growth is only about 5 grams of protein per day. But we have everyone, whether you're 16 or 65, has a turnover of 250 to 300 grams of new protein per day. Basically, every protein in the body has a half-life, and some of the proteins in the liver only last an hour or two, while some of the proteins in muscle last 30 or 40 days. So we have this constant sort of repair or replacement going on. And that's really, why we need to pay attention to protein synthesis, protein turnover. How well we do this process of protein turnover really has a lot to do with long-term health and aging.
Yeah, that's a good segue. We hear a lot about the need to maintain muscle as we grow older. Back in the 70s and 80s, when you were just sort of beginning your career, there wasn't a lot of focus on this, other than athletic performance perhaps. Largely because of some of your research and that of others, we now know that protein is critical in terms of helping people stay in good health as they age. Can you give listeners a sense of just how important protein is for health span and aging?
There were a couple of major discoveries in the late 90s. As you point out, we used to think about muscle, and it was for kids for development or athletes. But in the late 90s, there were two big discoveries. One was at the University of Texas in Galveston by Bob Wolf's group, and they discovered that as we get older, the efficiency of our ability to repair and replace protein goes down. They did a great experiment where they looked at giving 25-year-olds a 15-gram protein meal, sort of comparable to a large breakfast or a small lunch. And they found that the 25-year-olds had a very robust response of protein synthesis. They gave the same meal to a 65-year-old and got no response at all. They went on and did another set of experiments where they increased the protein to double that up into the 30s. And what they found was that the younger individual didn't get any additional response, but now the 65-year-old responded just like the 16 or 25-year-old. So what we know is the efficiency is going down. And about at the same time, my research group discovered that the regulation in muscle was particularly related to what we call a couple of initiation factors. Names aren't particularly important, but it was EIF4 and S6 ribosomal proteins. We found that those were key regulations, and they were sensitive to the amount of protein and particularly essential amino acids in the diet. So with those two pieces, what we realized is that to maintain muscle health in adults, what we need to do is increase both the quantity and the quality of the protein. And if we do that, we can protect muscle as we get older.
I think what you just described is the beginnings of now what we call anabolic resistance of aging. Any more comments you'd like to make on that?
Yeah, that's exactly right. We have always known that when you get into your early 40s, we begin what one might consider a downward track of aging, whether it's bone health or muscle health. We tend to have some losses, and we tend to be weaker in our 50s or 60s or 70s. And that's sort of the aging process. We have this anabolic resistance that we've now discovered that we can kind of blunt that process if we just increase the protein. We can overcome that anabolic resistance, again, with enough protein of the highest quality.
Some people might be surprised by this, but I understand that you've learned that this inefficiency actually often begins in our 30s. Isn't that right?
The regulation of protein synthesis in muscle is fairly complex. The key regulation is a complex known as mTOR. It's a mechanistic target of rapamycin. It's a protein complex in muscle, kind of like Grand Central Station. And it senses different things, at least 4 different inputs. One of those inputs is hormones. And when you're young and growing, the muscle is very sensitive to hormones, and it will grow, frankly, even with a relatively poor diet. But after we get through our growth period into our 30s, and certainly by the time we're 40, now this system is more resistant. And what we now know is it's much more sensitive to the other inputs, which are energy, protein, particularly in the form of an amino acid known as leucine, and resistance exercise. So this mTOR complex is coordinating all 4 of those inputs. When we're young, it's dominated by the hormones. When we get older, it's dominated by protein quality, and particularly that amino acid leucine. So anabolic resistance, when does it start? We did a few experiments showing that it really is evident in the mid-30s. So we can show that we're beginning to get resistance, and we're becoming much more sensitive to protein and even things like meal distribution of protein in our early to mid-30s.
Okay, so now let's talk about what constitutes the right amount of protein. There is lots of confusion and mixed messages on this issue. Much of it might be because of the Food Pyramid's recommendation of a daily allowance for 0.8 grams per kilogram of body weight. Can you help our listeners navigate this? This seems like a remarkably low amount.
The recommendation for 0.8 grams per kg is part of a range for every nutrient, whether we're talking about protein or vitamin C. The National Academy of Science has recommended a range of intake. And so we know that the minimum amount to prevent a deficiency, for example, of vitamin C is 60 milligrams. But, for common cold or during COVID, people are very comfortable taking 1,000 milligrams. So 10, 15, 20 times higher. For protein, the 0.8 grams per kg is that RDA, which is defined as the minimum level to prevent a deficiency. I don't think most people are after minimum health. What we want is optimum health. And the range for protein actually goes from 0.8 grams as the minimum up to around 2.5 grams per kg. So what we now know is for most adults, the healthy range is probably between 1.2 and 1.8 grams per kg. And that's usually where we recommend, somewhere around 1.5 grams per kg, which translates into about 0.7 grams per pound.
That sounds right to me as well, and it seems to be what is increasingly pointed at in the literature. I've heard you talk about how 40% of women who are 60 years old or older consume less than the RDA for protein, which is certainly not optimal itself. Please talk about this unfortunate situation, and one sees it all around us when we interact with older people, particularly older women. Could you talk a little bit about this?
There's this myth out there that everybody in the United States is eating too much protein. But if you look at our national surveys, a lot of people, particularly women, are very close to that minimum RDA. What we know from the NHANES survey, which is the USDA's national food survey, is that of women over 60, nearly 40% of them are actually below that minimum RDA. And on the other end of the spectrum, young women who are between the 16 and 22 age, it's almost 20% are below the RDA. So women in particular are functioning very close to the minimum RDA. And then when you start layering things like plant-based diets, plant-based proteins, which are poorer quality together with it, there's a lot of women who are very much in risk for some sort of protein deficiency, which again is sort of the aging loss of functional mobility, metabolic health, and just overall muscle health.
Absolutely. And one still hears people, particularly physicians, saying that high-protein diets aren't good for you and that too much protein, whatever they think too much is, will surely ruin your kidneys or some other aspect. I'm sure that you don't share that concern, but do you have any thoughts on that?
Yeah, there's always been these thoughts out there that high protein was bad for your kidney. The research has totally rejected that. In fact, again, the National Academy of Sciences, when they actually looked at it, said that low protein diets are actually more damaging to the kidney than high protein diets. Higher protein diets actually maintain your kidney size and filtration rate much better. The origins of that belief is people with advanced diabetes and renal failure. What we know is if the kidney has actually failed, if it's no longer functioning, you really do have to lower the amount of solutes in your diet. And that's salts, but it's also protein, which, produces urea, which has to be eliminated in the urine. So for normal, healthy people, low protein is actually worse. The other aspect of it is people say, well, protein's bad for your bone. That has also been rejected. We know that protein actually is the best way to maintain bone health. So there's a lot of myths out there. And unfortunately, physicians are one of the origins of the myths. They keep repeating it, and it sort of reflects how little nutrition training they have in their medical training.
Absolutely. It's rather amazing when one thinks about it.
Yeah, it is. So 1.2 to 1.8 grams per kilo, that's a good range and a good target probably for most all ages. Let's talk a little bit about the quality of the protein within that range that would be sort of optimal. Some people may disagree, but it seems that carnivores and omnivores can get the right quality and quantity of protein much easier than vegans, perhaps. And this is in part because the amino acid leucine is vital for tissue repair and regeneration across all cell types, and leucine levels are really low in plant-based foods. Can you talk about sort of the difficulties of vegans and vegetarians in having consumed enough high-quality protein daily?
One of the things to keep in mind is the RDA, that 0.8 grams, that minimum number, is actually defined with young males consuming an exclusively animal-based protein diet. So it's very high quality. What we know is that, as you pointed out, plant-based proteins, they actually have amino acid patterns based on the plant. And plants have different amino acid needs than humans. They're building leaves and flowers and roots, which are pretty different than brains and hearts and muscles. And so they're not the right proportion. And we have evolved to really use animals to correct that plant proportion. And you point out one of the amino acids that's really key to this is leucine. If we think about two proteins that people might be familiar with, whey protein has almost 12% leucine in it. So you can meet your leucine need for muscle protein synthesis with as little as 23 grams of whey protein. Soy protein, on the other hand, has about 6.8% leucine, so it takes almost 33 grams. So you can meet your leucine requirement with a plant-based diet, but it always is going to take more total protein, usually at least 30% more. So one of the problems you tend to see with plant-based individuals, people who go more vegetarian, they decrease the quantity of protein they eat, but they're also decreasing the quality at the same time. So they become severely at risk for deficiencies of the essential amino acids.
We hear a lot of talk these days about the need to adopt a more plant-based diet, but you are on the record as saying we already have a plant-based diet. Would you expand on this a little bit for the listeners?
Yeah, I mean, you referred to the food guide pyramid earlier. That was a plant-based diet. And what we saw is that there was a decrease in consumption of high-quality proteins, of dairy products, of eggs, of beef, by about 35% back in the period from 1980s to 2010. And what people replaced it with was grain products, particularly wheat. So at this point, Americans are getting well over 80% of their plant-based proteins come from wheat. And if we look at total calories, Americans are getting over 70% of their calories from plant-based calories. And a lot of it's coming from highly refined oils and sugars and refined grains. So, my argument is always, we don't need a more plant-based diet. We need a diet with better plants. People aren't eating broccoli and green beans and avocados. They're eating processed breads and cereals and sugars.
Can you talk about this plant-based diet you just described in the context of the obesity epidemic?
There's been a lot of discussion of that. If you look at the obesity epidemic, it almost exactly coincides with the advent of the food guide pyramid. The food guide pyramid came in the late 1980s, and that's almost exactly where you can begin to track the obesity epidemic in the U.S. We know that eating, the sugars, eating the refined grains, eating all of the breads are really a stress on the body in terms of our glucose, our blood sugar regulation. And so there's a lot of individuals who, myself included, believe that the origin of the obesity epidemic is eating a lot of carbohydrates. We're eating probably more than twice the amount of carbohydrates that we can justify in the American diet.
So let's switch gears a little bit now and go back to some of the discussion you started to have earlier about signaling mechanisms involved in muscle protein synthesis. I'd like to talk about a couple of your earlier studies, some of which are highly related to chronic disease as we think of it today, type 2 diabetes, metabolic syndrome, and so forth. First, let's talk about the 1998 paper that set out to define the role of protein in regulating muscle protein synthesis at the level of translation initiation, which is, of course, a rate-limiting step. Can you walk us through this study and its significance at the time, given all the work that's happened since 1998? It was clearly an important step forward.
Back when I was ending graduate school back in the late 70s, there was a lot of work with people beginning to look at essential amino acids and protein synthesis, and there was some work that surfaced about leucine, the amino acid we talked about. But after that, as the techniques were evolving, everybody was looking at the liver regulation, and they were looking at a regulation factor known as EIF2, initiation factor 2. And my group realized that in muscle, that could never be limiting. That was one that was limited really by energy. And the muscle is really never limited by energy. It has too much of that initiation factor around. And so we basically took a leap of faith and said, we think it's going to be EI of 4, initiation factor 4, that's going to be more sensitive to diet, and particularly to leucine. And so we ran a series of studies back then to look at that regulation. And what we were the first to report is that when an individual was under stress, we happened to be using exhaustive exercise. When the individual had a catabolic condition, they were under stress, protein synthesis was down-regulated. The way we had to use to recover it was basically using protein, high-quality protein, and specifically the amino acid leucine. And what we showed was that it basically stimulated those initiation factors and turned on muscle protein synthesis. A lot of research in the next 20 years. We now know extensively of how that mechanism works through a molecule I mentioned earlier, mTOR. We know about the multiple regulations that come from leucine, come from hormones like insulin, energy through a molecule known as AMP kinase, and exercise through a regulation known as RED1. So the muscle is actually integrating all of these different inputs, and it turns on protein synthesis when they're all correctly balanced.
That was definitely an interesting and important study, which you followed up with a parallel article that showed the link between protein, specifically again leucine, to translation initiation factors. Can you walk us through the significance of this study, which appeared in the Journal of Nutrition and was titled Leucine Supplementation Enhances Skeletal Muscle Recovery in Rats Following Exercise?
The first study that you mentioned in 1998, we did it basically trying to look at protein versus carbohydrates and fats. So we were really looking at the macro level, the macronutrient level, and people were arguing about the importance of carbohydrates for recovery and things like that. And what we showed was protein. The next study, we went the next step and we looked at the essential amino acids, and we showed that the specific effect of protein was actually specific to the amino acid leucine. So this really made the next step forward that leucine is a very unique signal that the muscle has evolved to look at. Leucine is part of a family of 3 amino acids known as branched-chain amino acids. And what's unique about those is most amino acids are metabolized in the liver, but these 3 are metabolized in muscle. And so when you eat a meal that contains protein in it, the muscle sees leucine in exact proportion to what it is in the meal. All the other amino acids get metabolized in the liver, and you don't actually see them in the blood in the same proportion. But leucine shows up exactly in proportion, and muscle has evolved to recognize that as a signal that, hey, this meal has the right amount of protein, the right amount of amino acids, and we can stimulate this very expensive process known as protein synthesis, protein turnover. So leucine became a very unique signal that we discovered, and that, has evolved over the last 20 years to basically the way we think about creating meals now. How much protein do we need at a breakfast meal? How much do we need at a lunch? And it really relates to the amount of leucine in the meal.
Let's loop back and discuss the master regulator of protein synthesis that we talked about earlier, mTOR. We have had a number of guests on STEM Talk discuss mTOR, including David Sabatini in episode 70, whose research in 1994 led to the discovery of mTOR. mTOR, as many of our listeners know, stands for the mammalian target of rapamycin, or in some circles today, the mechanistic target of rapamycin. Some other interviews on STEM Talk that discuss various aspects of mTOR include Keith Barr, episode 62 and 63, and Matt Kaberlein, episode 139. Don, could you give our listeners just a brief primer on mTOR? You started on it earlier, but a little more on mTOR, particularly as it relates to protein synthesis.
Absolutely correct. So David Sabatini really is sort of the guru of mTOR. He has done the majority of the work. So we sort of got the ball rolling relative to muscle. Sabatini and most of the people who work with mTOR and the mechanism have used liver or cell tissues. We took the step and actually applied it to an important tissue of skeletal muscle. So we were the ones that really linked it to muscle as a regulation. as I mentioned, mTOR is regulated by different inputs. And so in liver, it's heavily influenced by energy. I mentioned AMP kinase and insulin, and also about amino acids. In skeletal muscle, it's more regulated by amino acids and by another molecule that I mentioned, RED1, which is sensitive to resistance exercise. So when people talk about mTOR, they tend to generalize it as if every tissue responds the same, but muscle responds very differently than liver or, another area would be tumor cells or things like that. And so there's a lot of people like myself who are very positive about the mTOR regulation. That is a critical step in keeping muscle healthy. But there are other people who are negative who say, well, that leads to aging problems and tumor promotion and things like that. And my argument would be, but they're not connecting the dots on the tissues. The tissues are responding differently, and we have to have the nutrition to back it up. We have to do nutrition correctly for muscle and not do it incorrectly for other tissues.
Yes, and there's a difference between chronic activation of mTOR and pulsatile activation as you're envisioning. And I think the groups often are talking right past each other.
That's exactly right. Most of the people who are talking about negative aspects of mTOR are using animal models, mice or rats, that are what we call ad libitum fed, which means they eat 24 hours a day. You can actually look in the stomach of a rodent in the middle of their sleep period, and their stomach is full. I mean, they're still absorptive, which means that they're chronically keeping mTOR active. And I think that's a negative. When we talk about mTOR in muscle, we want to have discrete meals. I think one of the worst things people can do in life is eating lots of small meals. That's kind of a concept that evolved out of more vegetarian type of eating because they're always hungry. But if you're really trying to maximize muscle health, what you want is discrete meals, 4 to 5 hours apart, 3, possibly 4 if you're trying to gain muscle mass, meals per day.
Yes, I think that's a good description with the excitement around the off-label use of rapamycin for inhibiting mTOR, and I appreciate that, and I can see why they're excited about that. A big group of people, as you noted, have ended up with the idea that mTOR is somehow bad. So I think your point is well taken.
STEM Talk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research organization investigating a broad range of topics aimed at understanding and extending human cognition, locomotion, health span, resilience, and performance.
Let's switch gears now and talk about your weight loss studies. In 2005, you had a paper titled Dietary Protein and Exercise Have Additive Effects on Body Composition. This was a fascinating study because it demonstrated the synergy of protein and exercise. Please walk us through this study.
When we discovered the effects of leucine and we knew the Galveston group effects of protein, we started putting all those pieces together. And in the late 90s, when these discoveries, it was the period when there were things like the Protein Power Book and the Zone Diet and the Atkins Diet were all coming out. And I thought, the reason that these things are working isn't so much the carbohydrate argument that were, prevalent in those, but it's a protein argument. So we designed a series of weight loss studies based really to, we talked about aging earlier. And if you think about muscle loss during aging, it's about maybe 5% per decade, maybe 8% per decade, which is a pretty small thing and very difficult to study. So we thought the way to study the effect of protein on muscle was really in weight loss studies, where you're trying to get an acute weight loss, but you want to spare muscle. So we basically designed our studies using what we knew about leucine and protein synthesis in muscle, and we started doing weight loss studies. Our first study was just a diet study, and what we found was that if you used a higher protein, lower carbohydrate diet, and our comparison was actually the food guide pyramid, which is a high carb, low protein diet. So we're comparing those two. What we found was that the higher protein would reduce muscle loss during weight loss. If you just give a high carb, low protein diet during weight loss, 35 to 40% of the weight loss will actually be lean tissue. And that's why people aren't successful with weight loss. They lose all this lean tissue, their bodies are less capable of burning calories, and they regain it. So we showed that a higher protein would reduce that dramatically. So then we just thought, well, how about doing resistance exercise? We'll do a diet and exercise and what we called a 2x2 experiment. So we had food guide pyramid, high carb, low protein with exercise. And this was middle-aged women who were overweight. They were doing 3 days a week of resistance exercise and 5 days a week of some walking, so aerobic exercise. And then we had a high protein, low carb diet and also an exercise group, 4 different groups. What we found was the individuals doing the carbohydrate diet alone, the food guide pyramid, 35% of their weight that they lost was lean tissue, a lot of it muscle. When we added in the exercise, we reduced that to 25%. So the exercise was very beneficial. We then did the high protein, low carb, and we found that they got exactly the same 25% loss was lean tissue. So they got exactly the same effect as the women doing 5 days a week of exercise plus 3 days a week of resistance. And then we added in the exercise onto the protein group, and we found that the lean tissue loss was only 7%. And so we basically showed that exercise has an additive effect, but when we compound it with higher protein, it's synergistic. It basically reduced the lean tissue loss to almost nothing. And so now basically the women were losing almost exclusively body fat. And we did a follow-up 1-year-long study. We found that they were far more successful and were able to maintain it far longer.
So, Don, you hit on something that I think is really important for the listener, and that is not just the efficacy of the weight loss, but the maintenance. Can you talk a little bit about this protein diet and exercise combination for maintenance of weight loss?
Yeah, there's a lot of data about, people can lose weight. I mean, you can go on almost any crazy diet and lose weight, but most people will gain it back. And frankly, they tend to gain back even more weight than what they lost. We refer to this as yo-yo dieting. You lose it, you gain it back, you lose it, you gain it back. We always felt that one of the underlying issues of that was losing too much lean body mass. We did a series of studies with animals where we would look at that, and we showed that when they lost a lot of lean body mass, and particularly muscle mass, they would burn a lot fewer calories, and they were more likely to gain back body fat. Adults have a real difficult time gaining the protein, gaining the lean tissue back. So I think that was really the underlying fact that by going to a higher protein, reducing calories and carbohydrates, we were able to target body fat for the weight loss, maintain the lean tissue, which is really the calorie burning furnace of the body. And so now these people, as they lose weight, they also don't have to reduce their calorie consumption. They can maintain it later on. They're much more likely to be successful long term.
Yeah, we did a trial, a very similar trial when I was at University of Alabama, Birmingham, found the same thing. Resistance training in the weight maintenance phase after loss is really, really beneficial.
Exactly. If you can maintain, a colleague of mine, Dr. Gabrielle Line, and I coined the concept of muscle-centric health. We think that if you can maintain your muscle health, not only for functional mobility, but it also allows you to burn carbohydrates. It allows you to burn fats. When we think about blood health, muscle is really the voluntary part of that. The brain, the heart, the liver, they burn basically calories at a very steady pace. There's not much you can do about it. Muscle's the voluntary part. And if you lose muscle, because of weight loss or bed rest or just simply aging, you become less and less able to burn those calories. You can't maintain your blood glucose. You become insulin resistant. We're more likely to see diabetes. So all of those things, we think that a focus on muscle is really the way to protect long-term health.
So two other great advantages of protein are the thermogenic aspect as well as the satiety aspect. People feel more satiated often after consuming a meal with substantial protein. Could you talk a little bit about both of these?
Both of those are important, and we saw both of them in our research studies. Those weren't really the outcomes we were after. We were after the changes in body composition, but we know that protein early in the day produces higher satiety. People are less likely to be hungry. Some great work by a colleague of mine, Heather Leidy, University of Texas. And what she has shown is that bringing protein into breakfast, getting 30 to 40 grams of protein into breakfast, makes you less likely to snack during the day. Americans tend to eat because we're kind of social beings and we're kind of programmed. And what most researchers have found is that basically high protein doesn't prevent you from changing your lunch. You're still going to have your lunch, but what it makes is you're less likely to snack in between. She did a lot of work showing that people were less likely to snack at night. So we think the satiety effects are that the meals are more satisfying, they're more satiating, and basically you're less likely to snack. The thermogenic aspect is an interesting one. We know that protein just burns away more calories than carbohydrate or fat. Of the calories that you take in from carbohydrate or fat, about 5% of it is lost as heat, where with protein, the calories, about 20% is lost as heat. People have argued over the years or projected over the years as to what's the cause of that. And they say, well, protein's more difficult to digest and absorb, and you have to make urea. So, it's just more costly to metabolize. We don't think that's the issue at all. Our research has shown us that we think it's really back to muscle protein synthesis. Muscle protein synthesis is a very expensive energy process, and the more times you turn that on per day, the more calories you burn. We basically did an animal study that showed that just simply moving protein into breakfast, bringing the amount of protein into a breakfast meal, had the same thermogenic effect as an hour of treadmill running for the rodents. Basically, it burned and so, which is easier to do, have protein at breakfast or go do an hour of treadmill running? Almost the same energy expenditure.
That's a good segue into a discussion about the interaction, again, between exercise and protein intake. So if someone corrects their protein intake as sort of step one, what are your thoughts about what they should do about exercise training? What kind of workout should people do to help build muscle? Do you think the focus as we get older should be on resistance training, muscle building, or more on endurance type training? There's a lot of controversy out there in terms of how do we improve or maintain cardiorespiratory health. Most would point toward some form of aerobic or endurance training, but then there's the whole muscle sparing effect and hopefully some muscle building benefits as we age too. So what are your thoughts about the approach as we get older?
There's no question that exercise is really critical for a muscle. Protein is part of it. Some people will say, well, I'm not going to exercise, so, at least correct the diet, use the protein part. But we certainly are big fans of the exercise. And as you started your question, I think it's important for people to think about, is the issue muscle building or is it muscle maintenance? A lot of people will say, well, I don't want to build muscle. I don't want bigger muscles, and therefore I'm not going to lift weights. We know that as we get older, there's a tendency to lose muscle mass. And we know that the solution to that is really resistance exercise. And as you were pointing out, exercise takes different forms. It can be resistance exercise, which means you're doing some sort of a contraction against a resistance, or it can be aerobic, which is more cardiovascular. We think both are critical. We think you need both things, and they're really different. We typically recommend 2 to 3 days a week of some type of resistance exercise, and right away, middle-aged women will say, I don't want to go to a gym. And so the point is, it's a restriction, it's a resistance. And so yoga or working against a rubber band, or doing something at home against your own body weight, getting up out of a chair, walking steps. Those are all resistance. Those are power exercises versus just going out and walking around the neighborhood. We always recommend, and I personally recommend what's called HIIT exercise, high intensity interval training. What I'd like to see people do is when they go out to exercise, get a combination of something that raises your heart rate. To really get a cardiovascular benefit, you have to increase your heart rate above 110 beats per minute. People will go out and say, well, gee, I walk for an hour per day, but they never raise their cardiovascular. I mean, they're burning some calories, but they never really stimulate their heart and vascular system. So we want an aerobic exercise. It can be fast walking. It could be riding a bike. It could be swimming. But we want some aerobic exercise that raises your heart rate. And then we want resistance exercise. Could be lifting weights, but it could also be yoga or Pilates. We want those two things for just muscle maintenance as we get older. If you're an athlete, and you're trying to actually gain muscle mass, now the resistance is the key, and you have to keep increasing the weights. You have to have more and more weight to make the muscles, to hypertrophy the muscles.
I want to emphasize that it's never too late to start resistance training. Marcus led a clinical trial back in 2011 when he was at the University of Alabama, Birmingham, that showed how men and women in their 60s and 70s who underwent supervised weight training developed muscles that were as large and strong as those of the average 35 to 40-year-old. It was a rather amazing outcome. Marcus, could you share with Don and our listeners how this study demonstrated that the neuromuscular system of older adults could be robustly responsive to resistance training?
Sure. This was an exciting study. This was an NIH-funded clinical trial, and it was really about young versus old, and those were the two age groups Ken just mentioned. And this was building on this idea of anabolic resistance, and could we overcome it in the older adult? And Don, you sort of hit on it earlier when you mentioned intensity of contraction and sort of intensity of resistance training. I think, at least in our experience, that's been a key element for both young and old. But this was one trial that demonstrated that the older muscle, even though there may be some anabolic resistance at the level of nutrient sensing and initiation, you can overcome a lot of that with intensity of training. We did protein turnover studies with tracers, and we looked at a lot of the signaling factors and initiation cascades. And the older muscle responds really well. It just needs the stimulation. But I will say in a follow-up, when we tried to actually optimize dosing for the older adult, the key element that we found that differentiated young versus old was not the tolerance to higher intensity training, it was the work-rest relationship. So we found in the older adults, if we intensely trained them twice a week and then had one lighter day, that was of greater benefit than actually intensely training 3 days a week, where the young people can tolerate that quite well. So I don't know if you have any thoughts about that, Don, but those were a couple of studies that I thought were sort of eye-opening for prescriptive dosing for the older adult.
I think those studies are really exciting, and there have been others that have sort of followed up on it. If you look back in the late 90s, there was concern about muscle and obesity. We were seeing more obese adults, and the concern was we knew that there was muscle loss during some type of a dieting, and there was concern as to whether, should people over 60 ever diet? Should they ever try and lose weight because there was too much muscle loss? So the work of you guys, David Allison's a pretty good friend of mine, people at UAB and others have shown that you can overcome it if you do resistance exercise. I think the frequency, the number of days per week, the volume of the exercise are important questions. And I'm not sure we necessarily have all the answers there. But I think that it is true that a young person can tolerate a lot more intensity and a lot heavier doses than an older person.
This whole idea of trying to identify the proper dosing is really important, I think, for the field, for all age groups, and really probably boils down to the individual and how well they respond at the level of some of the metabolic pathways we've been discussing today. It's probably a good place to talk about timing of protein intake relative to bouts of exercise to get the maximum benefit of that protein. Can you talk a little bit about that?
That's an area that we kind of discovered and to some extent probably misled people. So the original Journal of Nutrition paper that Ken mentioned earlier in our talk, what we used to depress muscle protein synthesis was exhaustive exercise. So the very first studies were done in rodents. We used treadmill exercise, and we knew that we could acutely turn off protein synthesis. We knew that we could do it with fasting, but protein synthesis is regulated in two different levels. It's regulated at the initiation factor, but it's also regulated at the gene level, what's known as the transcription factor. And when you get further into a fast or starvation, it's really more the gene level. So we wanted some way to really look at it at a very, within an hour. We wanted to shut down protein synthesis and then look at recovery. And so that's how we did it. And what we showed is that we could shut down protein synthesis, we could give protein or we could give leucine within the next hour after finishing the exercise, and we could get an instant recovery. That sort of got into the literature as you should time protein to have it right after exercise, or some people even started looking at it during exercise. That really wasn't the point. The point we were showing is that leucine and mTOR is a recovery from a catabolic period. And all of the exercise studies that have looked at it have been untrained individuals doing an acute exercise bout, and you can use leucine or protein and show rapid recovery. However, if the person's well trained, the activity really won't be that catabolic, and the timing doesn't become very important. They can have their next meal 10 hours later, 20 hours later, it doesn't really matter. They'll get the same recovery. So there's a difference here in timing. If you're just starting a training, if it's an acute training and it's catabolic, first week, 2 weeks of football practice for high school kids, having protein right after is probably a good idea. If you're well trained at the activity, I don't see any real benefit to that. You can do it if you want, but if your next meal's 3 or 4 hours later, that's going to give you all the benefits you're looking for.
Yeah, I think that's a very practical way of looking at this, thinking sort of teleologically about hunting and gathering and when protein was made available. I mean, if you just get it in, at some point in the day, get it in. Let's talk a little bit about metabolic transformation. This whole idea that you've established where diet is truly a 4-letter word. So I want to hear you talk about metabolic transformation, the website, what you've done with your former student, Dr. Gabrielle Lyon, on the concepts of muscle-centric health and protein-centric diets. Can you talk a little bit about this?
Well, thank you for bringing it up. My thinking has always been that muscle was really a key, and it's a part of the body that we have voluntary control over. People always get concerned about heart disease and therefore the heart, or cancer and some sort of tumor or other organs. I've always felt that muscle really was the key. The body, when we think about diet and exercise, the two tissues we really need to focus on are muscle and the brain. If we get the nutrition right for those two tissues, everything else is regulatory. Everything else falls in place. When Dr. Lyons and I started looking at those types of things, we realized that our major health problems with obesity, with diabetes, with heart disease, even with Alzheimer's, all related to how the body regulates these macronutrients. How do we handle blood sugar? How do we handle fatty acids? How do we handle insulin? And muscle really is the key to that. So we developed the concept of muscle-centric health. And if you can keep your muscles healthy, then you can rebalance the protein, carbohydrate, and fat in the diet. Now you've got a real shot at long-term health. So, people get way out on a limb about, well, it's all about fat, or it's all about carbohydrates, or too much protein, too little protein. It's really about getting the right balance to sustain your muscle and your brain. And if you get those two right, chances are you're going to have a long, healthy life.
So this idea of a diet isn't really a diet of, but an overall program or a way of thinking and a way of approaching this. And you made that pretty clear, I think, from the get-go on the website and the program that you've developed. Can you talk a little bit about, you mentioned earlier this whole idea of yo-yo dieting and the problems associated with that. I think we'd like to revisit that for a second and just expand on sort of this metabolic profile and people who sort of struggle with maintaining a healthy profile and sort of relate that to muscle metabolism as part of the fix.
Yeah, I'll go back to that. One more thing about the website. The website really originated out of people asking me for access to our research. So one of the things that I know as a researcher is that we basically discover things, we write it in scientific literature, and it may take 10 or 20 years before that ever gets to the public. So I had people saying, well, how can I access your diet? How can I find the things? So we put together the website, Metabolic Transformation, to really allow people to access what we were doing. And so that's sort of the origin of it. I think, as we were looking at that, we really got invested in thinking about the carbohydrate to protein ratio. Most people in the United States are overeating carbohydrates. We have a carbohydrate need of about 120, 130 grams of carbohydrates per day. The actual RDA for carbohydrates is 130 grams per day for adults. The average American's eating almost 300. So we're eating nearly 3 times our RDA for carbohydrates. And people say, well, you're eating too much protein. Well, we're eating way too much carbohydrate. And the way I sort of link it back to the muscle aspect is that we have a basic need for carbohydrate, blood sugar, for the brain and red blood cells and kidneys. They're what we call obligatory glucose users. They use blood sugar. But then muscle is sort of the voluntary, and you earn carbohydrates at about 40 to 70 grams per hour of exercise in this sort of intensity. If you're just going out and walking for an hour, kind of a brisk pace, you can maybe eat another 40 grams per hour. If you're doing higher intensity, maybe 60 grams. So we usually say, well, okay, if people are exercising, an hour per day, they're now 120 plus 60, they're now up to 180 grams per day of carbohydrate, which is frankly kind of in the range that I eat. But people are eating 300 grams. That means to justify that, they have to have 3 hours of intense exercise per day. And there are very few adults doing that. And that really is the origins of obesity in my mind. We're eating far more carbohydrates than we need. We have to store it as fat. It's also causing problems with insulin, leads to prediabetes and diabetes. So to me, those are where the epidemics of these diseases are coming from.
Don, that's a great explanation. Could you walk people through what happens at night while we sleep and why protein in the morning, as you've mentioned earlier, is so critically important that your first meal have a substantial bolus of protein?
The piece of information that everybody needs to recognize is that, as I mentioned earlier, muscle protein synthesis is a very expensive process, so it doesn't run very long. If you have a protein meal, it might even be a high protein meal. Maybe you have you have 8 ounces of beef, a high protein meal. Protein synthesis in muscle will only run about 2 to 2.5 hours. And so the average American is getting 70% of their protein in one meal, dinner. And so the rest of the time, they're catabolic. You have 1 2-hour time per day that you're anabolic, protein synthesis is occurring in muscle, and then the other 22, you're catabolic. And so as you go from dinner into the nighttime, the person becomes more and more catabolic. One of the things that we mentioned earlier was that every tissue in the body has protein turnover going on. In the liver, in the middle of the night, when you haven't eaten for 10 hours or so, your liver still has to be making protein. So where does it get the amino acids? How does it do that? Well, the body has no storage for amino acids, so it gets it from muscle. Muscle goes into what we call as a catabolic period where it's breaking down. It's supplying amino acids to the liver and the kidney and the brain and things that have to run during the middle of the night. If your liver stops making protein in the middle of the night, you die. So you have to go into this catabolic period. So that means when you wake up in the morning, you've now gone through a 12-hour period of breaking down your muscle. And if you then don't eat protein until dinner, you spend another 8 hours breaking down your muscle protein. So we now recognize that breakfast, that first meal after you come out of the overnight fast, is a very important protein meal because now you're rescuing your muscle protein. You're basically shifting it from that catabolic period back into an anabolic period to rebuild and repair your muscle protein that you damaged, frankly, during the night. And we think that's a really critical thing during aging, but during stress times like weight loss or bed rest, we have to front load protein in the day to correct that catabolic period of nighttime.
So when you think about how much protein for that first meal of the day, I know you've made some comments about 40 grams is a good number to start your day. For that's about 6 large eggs, right? That may sound like a lot for some people. So if you consume on a consistent basis about 40 grams for breakfast in the morning, tell the listeners how you achieve that.
So we know that to come out of that catabolic period, you need somewhere between 2.5 to 3 grams of leucine. So that kind of depends on what the protein's going to be. I mentioned earlier that whey protein, you can get 2.5 grams of leucine from about 23 grams of whey protein. So a protein shake is a good way to go. If you actually look at our website, my website, we have a protein shake there that is designed for a meal replacement for breakfast. So I frankly had a protein shake this morning before my exercise. If you're going to other kinds of foods, you have to go to more protein dense. You mentioned eggs. Eggs are a good source, but meats are a better one. So we frequently would create something, it's sort of a takeoff on an Egg McMuffin type of thing, but you need to get about an ounce to about 2 ounces of meat, 2 ounces of Canadian bacon, an egg and a slice of cheese, half a slice of toast or English muffin, and a glass of milk, and now you'll have your 40 grams. So doing it purely with eggs, you can do it with egg whites, etc., but it takes quite a lot. If you're really going to do that at breakfast, we recommend you consider either some protein supplements or including some meat, something that is more protein dense, where you can get 4 ounces of meat will give you about 30 grams of protein.
Steak and eggs works great for breakfast.
Yeah, steak and eggs is great, So you can do it in different ways. And again, on the website, we have some of the meals that we use during the weight loss, and so there are examples there of how to create it. Again, I'm a huge fan of protein shakes just for the convenience, but when I have more time, I do exactly what Ken suggested, more of a meat and eggs kind of combination.
It works. How about dinner and lunch? I mean, what do you think in terms of how many grams of protein a person should aim for, particularly as they're aging and moving through life's curve?
We coined the concept of a 30-gram protein meal, and to some extent I regret that. What we know is that your sort of window, your sweet spot for protein in a meal is between about 30, again, depending on the quality, about 30 grams to about 55 grams. And so I typically try to recommend people get that first meal somewhere 35 to 40, whatever is convenient, but get it above 30. And the last meal, most people are comfortable with having a bigger protein meal, so I usually recommend something in around 50. I think that variety is good. The middle meal is an interesting one. There's actually no research looking at the effect of lunch. And we were talking a little bit ago about how long does a meal last? About 2 hours, you get an anabolic effect. But what we also know is in studying the mechanism, all of the signals are still active 5 hours later. So when you get to lunch, all of the signals to that mTOR molecule are still active. So how much protein does it take? I don't think there's anything particularly magical about it. I think 15 grams, 20 grams, 25, 30, I think whatever's convenient may be fine. So again, if people are aiming at 120 grams per day, they could go 40 at breakfast, 55 at dinner, and 20 at lunch. And I didn't do the math, but that's about 120.
Let's switch gears back to a topic that came up a little bit earlier in the discussion, which was intermittent fasting. Sounds like you're probably not a fan of that concept, given what we just talked about, and the fact that we all have an intermittent fast every night when we sleep. So given the sort of increasing popularity of intermittent fasting as well as time-restricted feeding. Can you just share your thoughts on those two approaches that many, many people are taking now to weight loss and weight maintenance?
I think intermittent fasting, time-restricted feeding, I'm actually more positive about time-restricted feeding. They're basically strategies to control calories. And so obesity is a major health risk. And if that's a strategy that can help you maintain body weight and control calories, I think it's a good idea. We then have to think about overall strategies. I think with aging Americans, I think that first meal should be earlier in the day. You want to shorten the amount of catabolic time. So another way of thinking about time-restricted feeding would be only eating twice a day, but eat at 7 and 7. Okay. I'm restricting the time I'm eating. I'm just not condensing them into a narrow window. I think that is another approach. And frankly, I often use that. I will have my first meal between 7 and 9, and I won't eat basically anything at lunch or very little, and then have another meal at 7 at night. That's a form of time-restricted eating for me that helps control calories. Fasting in general, I don't think anybody over the age of 35 should ever fast. And by fasting now, I'm talking about 36 hours or something like that. Because if you do that, you're going to start losing lean body mass. And unless you have a specific strategy for protecting lean body mass or regaining it, that's going to be a net loss long term. So, I don't think a 60-year-old should ever be fasting. And intermittent fasting, fasting one day a week, I think is just a bad choice. I think time-restricted feeding makes more sense. I think fasting's a bad idea.
Yeah, thanks for your insights on that. I think what you just described, a couple times a day, spread, essentially 12 hours apart, makes a lot of sense. I'm sure with this discussion, we've had a number of listeners who will check out your website to get more information after listening to this. Also, we know that, again, your former student and colleague, Gabrielle Lyons, has a book coming out that builds off a lot of this research that you two have done over the years. So can you tell us about that at all? Do you know much about her book, which is entitled Forever Strong, A New Science-Based Strategy for Aging Well?
Yeah, so Gabrielle and she was actually a student in my lab. She worked on some of the research studies, the human weight loss studies that you were mentioning. We have been really close friends and colleagues for years, and somewhat embarrassingly, the book is dedicated to me and our discussion. So it really is an outcome of this muscle-centric discussion, a muscle-centric health. She's managed to encapsulate it into a very lay-friendly discussion. I think it's available for purchase now. I think it's actually not coming out till fall, but it's a very good description in great detail about how to understand muscle-centric health and actually how to implement it. So, I have read it. It's very interesting to read, and it's great science.
Over the summer, you were in Boston to attend American Society of Nutrition meeting, and you were part of a panel discussion titled The Global Nutrition Transition, Improving Nutrient Analysis and Monitoring of Metabolic Markers. Could you give us some highlights of what was covered on that panel and how you think it went?
Yeah, it's an interesting time right now. In many ways, we're becoming more and more sophisticated about diet. In other ways, we frankly don't understand it very well. And one of the reasons we don't understand it is our databases aren't very good. And so the overall discussion was about these databases and how are we going to bring them together. The primary database about foods is the USDA legacy database. There's about 7,000 foods in that database. And in the US alone, there's 15,000 new products that come on the market every year. So you can see how outdated and frankly kind of useless it is. And so we're basically arguing, we need a much more sophisticated understanding of diet, and we need more understanding of plant-based diets. We need to understand the phytochemicals, the nutraceuticals that are in plants. My specific talk was about protein, and we had a new paper that just came out in Journal of Nutrition. It's time that we stop talking about protein and start talking about amino acids. People have said, well, people don't understand essential amino acids. People don't understand riboflavin or B6 either, but we put them on the label for transparency. People can look at the data. What we need to do is focus our understanding on how much of the 9 essential amino acids we need. As we talk about more plant-based diets, we're going to challenge where do we get these essential amino acids? And people need to understand that. One of the examples I like to use, and if we use a common wheat cereal, something like a wheat bran raisin cereal in the morning, you can look on the package and it'll say a serving is a cup of this cereal, 4 grams of protein, mix it with 6 grams of milk, 6 grams of milk protein, 6 ounces, and you have a complete dietary protein mix. It's exactly right. But people aren't recognizing that if you're trying to mix it with a soy milk, for example, it needs over 20 fluid ounces because the amino acids that are missing in both of them. Both the wheat cereal and the soy are low in lysine, methionine, and leucine. And so we need more transparency. So the symposium and the discussion was about we need a more sophisticated database about food if we're going to make the next step in advancing health.
That would be great. Don, now that you've stepped away from your day-to-day duties at Illinois, how are you spending your time? I know earlier this year you took a ski trip. Where did you go skiing, and did you think about the risk-reward ratio?
Not as much as I probably should have. I've had colleagues that I worked with in the Salt Lake City area. So I've been going out to Salt Lake City for about a decade now. And I actually have had a season pass at Alta and Snowbird for the last 5 or 6 years. So I usually get in 12 to 15 days of skiing out in the Utah mountains, particularly at Alta. And that's a pretty steep mountain. So I'm not sure the risk ratio is quite as good as I should at my age now. But yeah, I've had the time to indulge in snow skiing, which I hadn't done since I was in college. And I've gotten to be a pretty good scuba diver, and I play tennis 4 days a week. So yeah, I have a lot more flexibility for the physical activity part of my life. And I still get to maintain the science part and do the writing, but I get to do it when and what I like to do. Yeah,
that sounds great. I've adjusted on skiing my risk-reward ratio. My other house besides Florida is in Wyoming, and the Tetons are steep. And, I took a look. I was not sure about this.
I skied the Tetons with you once a few years back.
I remember.
And so I've skied that area maybe 3 times, but they're pretty serious mountains too.
Yeah, they were.
Well, if you injure yourself, just make sure you have enough protein for tissue regeneration.
Yeah, exactly. We know it for both bone health recovery or muscle health recovery that the exercise, the protein, the diet is critical for recovery.
Indeed.
Don, this has been great fun. Thanks very much for joining us today on STEM Talk.
Yeah, it was great, Don. Thanks a lot.
It was great fun. Covered a lot of topics, and hopefully your listeners enjoy it.
I'm sure they will. It's good to hear your voice again after all these years.
Absolutely. And thanks for the knowledge, thanks for sharing, and best of success with the website and all of the work coming up.
My pleasure. Great to be with you guys.
STEM Talk. STEM Talk.
STEM Talk. STEM Talk.
As you well know, Ken, I have spent my career looking into the ways that exercise, particularly strength training, can induce so many health benefits for people. So I thoroughly enjoyed this interview, especially Don's emphasis on muscle development, muscle protein synthesis, and his overall knowledge of protein metabolism as key levers that can improve people's health span.
Yes, Marcus. I hope today's interview helped listeners gain new insights into protein and how critically important it is in terms of healthy aging. As we grow older, our protein building processes become less efficient. Consequently, we need to eat more protein than the government's RDA of 0.8 grams per kilogram of body weight. In fact, way more. But another key point today, and one that I'm sure you appreciated, Marcus, is the need to tailor our workouts to focus on maintaining and building muscle. Improving our muscle function and metabolism are 2 of the most important things we can do for ourselves as we age.
Absolutely. So to all the listeners, if you enjoyed this interview as much as Ken and I did, we invite you to visit the STEM Talk webpage, where you can find the show notes for this and other episodes at stemtalk.us. This is Marcus Baumann signing off for now.
And this is Ken Ford saying goodbye until we meet again on STEM Talk.
Thank you for listening to STEM Talk. We want this podcast to be discovered by others, so please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.